In the last lecture, I have given the definition of walk, trail and path. Okay, now just I am giving the definition of cycle. So again I am repeating the definition of path. See, what is path? Path is a sequence of distinct vertices v1, v2, so on vk for every I less than or greater than or equal to 1, less than or equal to n, such that vi plus 1 is an edge in G, or vi is adjacent to vi plus 1. vi is adjacent to vi plus 1 for all I, for every I is greater than or equal to 1, less than or equal to k minus 1. As simply why this I have taken k minus 1, because here I have written I plus 1. Okay, so simply path is a sequence of distinct vertices. Note down that what is the difference between the trail and path. Path is any distinct sequence of vertices such that the two vertices are adjacent. The two adjacent vertices are in the sequence. vi plus 1 is an edge in G, or vi is adjacent to vi plus 1 for every I greater than or equal to 1 and less than or equal to k minus 1. Okay, suppose this is a graph, and here if we are writing a path, then simply there is a path like 1, 3, 4, 5. This is a one path P1 for this graph. I am talking about G3. Suppose this is a graph. Then the another path P2 is 2, 3, 5, 4. This is a path. Okay. But if we write, say suppose 2, 3, 5, 4, 3, 1. This is not path, as the vertex 3, there is a repetition of the vertex 3. So this is not a path in this graph. Okay. Now the next is what? Closed path. Closed path is a path in which the start and end vertices are same. Start and end vertices are same means it is closed. Wherever there is a closed, it means it is start and end vertices are same. So that is called closed path. Okay. So, and closed path is also called cycle. So in this graph, there is in a particular graph, there can be the number of cycles like 1, 3, 2, 1. This is a cycle 1 in this graph. Another cycle is C2 in this graph. G3 is 3, 4, 5, 3. Okay. One more cycle here, like it will start from C3, 2, 3, 1, 2. Okay. The same if we consider this graph. Suppose here, consider this graph. Okay. So in this graph there can be the number of cycle, like say suppose C1 is 2, 3, 4, 1, 2. 2, 3, 4, 1, 2. Another cycle is like 4, 3, 7, 6, 4. Okay. So simply the sequence of distinct vertices such that the 4 is adjacent to 3, 3 is adjacent to 7, 7 is adjacent, means there is an edge between 4 and 3, 3 and 7, 7 and 6, 6 and 4. And start and end vertices are same, then that particular path is called closed path or cycle. Closed path is also called cycle. Okay. There is one more term, that is circuit. Actually the circuit is nothing but the closed trail, what I discussed in the last lecture, the closed trail. So the circuit, what is the difference between the circuit and cycle? In the circuit is a closed path, or you can say that the circle is a cycle in which vertex can be repeated. Okay. So here if we find a circuit. Okay. So see in this particular graph, say this circuit is 1, 3, 4, 5, 3, 2, 1. See, here 3 is repeated. So this is circuit. Here in this particular graph, 1, 3, 4, 1, 1, 3, 4, 5, 3, 2, 1. Okay, so here the vertex is repeated. Again, remember that there is no repetition of edge. Edge is not repeated. That's why the circuit is also called closed trail. Okay, so circuit, this is a circuit. So the circuit is, this is a circuit, but it is not cycle. This is the difference between circuit and cycle. In circuit, vertex can be repeated. Edge is not repeated, but vertex can be repeated. In the cycle, vertex and edge both cannot be repeated except the first and last vertex. Why the first and last vertex? Because this is circuit or cycle, or you can say closed loop. If it is closed, then always first and last vertex is same. Okay, so here see, this is circuit, but this is not cycle. But if we consider this one, 1, 3, 2, 1. So this one, 1, 3, 2, 1 is a cycle as well as it is circuit. So every cycle is a circuit, but every circuit may or may not be cycle. Okay, so this is the definition of circuit and cycle. Now just here, come to the another definition. This is what related to our problem Hamiltonian cycle is Hamiltonian path. See, it is a path in an undirected or directed connected graph. Always remember that for Hamiltonian path, the graph should be connected. That visits each vertex exactly once. Now I am talking about the path that covers all the vertices, which path that contains all the vertices of the graph, that path is called Hamiltonian path. And as it is introduced by the Hamiltonian scientist, that's why its name is Hamiltonian path. Okay, so and Hamiltonian path sometimes is also called traceable path. Okay, so see, in the Hamiltonian path, if we consider suppose this graph, okay, if what definition tells that simply the first and last vertex is, the first and last vertex may be same, may be different, but here just it visits all the vertices exactly once, and it can start from any vertex. Okay, so suppose if we consider this graph and we start from 3, so 3, 4, 5, 3. Okay, so 3, 4, 5, and now just because the vertex cannot be repeated, 3, 1, and it should cover all the vertices. So here in this graph, no Hamiltonian path exists. In this particular graph, there is no Hamiltonian path. Same, there is a Hamiltonian cycle, the Hamiltonian path in which the first and start vertex is same, called Hamiltonian cycle. Hamiltonian cycle is also called Hamiltonian circuit, and a graph possessing the Hamiltonian cycle called Hamiltonian graph. Okay, so this is a very hard problem to tell whether a graph is Hamiltonian graph or not. In other words, in a given graph, whether Hamiltonian cycle exists or not, or simply the Hamiltonian. So in this graph, no, this graph is not Hamiltonian graph as there is no Hamiltonian cycle exists. Okay, now consider this graph. In this graph, if suppose first you consider this graph G3. Okay, so here if suppose we are simply starting from 2, so 2 to 5, 5 to 6, this is the graph. Okay, the graph is this. Okay, then 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1, and 1 to 2. So there is a Hamiltonian path. See, Hamiltonian cycle. Hamiltonian, first I am writing Hamiltonian path. Hamiltonian path, suppose I am taking 2. Okay? 2, 5, 6, 3, 4, 1. 2, 5, 6, 3, 4, 1. Okay? So just it widgets all the vertices exactly 1. So this is Hamiltonian path. Now Hamiltonian cycle for this graph. Suppose we start from 2. So 2, 5, 6, 3, 4, 1 and 2. Okay. So see, just all the vertices are different here. So this is Hamiltonian cycle. Okay. So in this graph, the Hamiltonian cycle exists. So this graph is called what? Hamiltonian graph. Okay. Now in a given graph, there can be the number of Hamiltonian cycle exists. Okay. So because we are going to solve this problem, we are going to find what are to print all Hamiltonian cycle in a given graph if it exists. And if there are more than one Hamiltonian cycle, then the backtracking algorithm will print all possible Hamiltonian cycle exist in the graph. Okay. So see, just before this, here. So one cycle, I have written that the Hamiltonian cycle HC1 is what? 2, 5, 6, 3, 4, 1, 2. This is one Hamiltonian cycle. Okay. If we consider Hamiltonian C 2. Okay. So if we write, say suppose 1, 4, 1, 4, 3, 6, 5, 2, 1. 1, 4, 3, 6, 5, 2, 1. This is another Hamiltonian cycle. See, the another Hamiltonian cycle is what? 1, 2, 4, 3, 6, 5, 1. This is another Hamiltonian cycle. Okay. Suppose if we consider this one Hamiltonian cycle like 1, 2, 5, 6, 3, 4, 1. Okay. So see Hamiltonian cycle 1 and this one. Okay. So this is nothing but what? The permutation 2, 5, 6, 3, 4, 1, 2, 1, 2, 5, 6, 3, 4, 1. Okay. So here simply just Hamiltonian cycle is what? Simply the permutation of n number of vertices. Okay. So here this cycle is different, this cycle is different, but the HC1 and the cycle 1 and the fourth one both are same. Okay. So we have to avoid generating the same cycle. So here just the widget, say 2 to 5, 5 to 6, 6 to 3, 3 to 4, 4 to 1, 1 to 2. So what we do, just to avoid the generating the same cycle again, we take the condition that our cycle always start from the fixed vertex 1. Okay. So here suppose in this graph I always take the start vertex as 1. So what are the different possible cycle like 1, 2, 4, 3, 6, 5, 1. This is first cycle. Okay. Now 1, 4, 3, 6, 5, 2, 1. This is a second cycle. This is a different from first. 1, say 1, 2, 1, 5, 6, 3, 2, 4, 1 and so on. Okay. So see, just for a given graph, first thing whether Hamiltonian cycle exists in a graph or not. This is a NP hard problem to check whether a given graph, it is a very hard problem, whether a given graph contains Hamiltonian cycle or not. And the graph which contains the Hamiltonian cycle, that graph is called Hamiltonian graph. Now here in our problem, our objective is that a graph undirected or directed, but the graph should be connected. Now see why I have written the graph is connected, because if the graph is not connected, then any path cannot cover all the vertices because it contains the disconnected component. So simply there is no adjacent vertex, so no path covers all the vertices in the graph. That's why here just our problem definition, the graph should be connected. If the graph is disconnected, then it is not Hamiltonian graph. So just here for our problem, input is directed or undirected but connected graph. Okay, and the backtracking algorithm will generate all possible Hamiltonian cycle if it exists. If it not exists, suppose the graph is not Hamiltonian graph, then the algorithm will not print any output. Okay. Now, so here just I have given all the definition, the path, closed path, cycle, circuit, Hamiltonian path, Hamiltonian graph and Hamiltonian cycle. Now the problem is how we solve this problem using backtracking algorithm. Okay, and see the algorithm is somehow similar to the graph coloring problem. Okay, what in graph coloring problem, just the solution vector is x1, x2, so on xn. Okay, where xi in the graph coloring problem, each xi represent the color of the vertex. Okay, here in the case of Hamiltonian cycle, solution vector will be represented in as a n tuple. Solution vector is n tuple, and here each xi is a vertex. Each xi is a vertex, and all in this solution vector, all xi's are distinct. Okay, see, if this is a cycle, then all xi's are distinct and x1 should be x1 equal to xn, because this is a cycle, so the first vertex and the last vertex should be same. And in order to avoid the same cycle again, so we take the condition that we always take x1 equal to 1. Okay, so here the solution vector, in this case the solution vector is n tuple. In this solution vector, the x1, x2, so on xn represent the distinct vertices, and as it is cycle, so the first vertex and the last vertex is same. And just to avoid the same cycle again, always I will take the cycle will start, every cycle will start from 1. Okay, so now the first is what are its explicit constraints. Okay, so here the explicit constraint, this is the solution vector. Solution vector is what? x1, so on, x2, so on xn. Okay, so here each xi is vertices, so simply xi belongs to simply vj. Okay, such that where vj is a vertex in, just you can say that here j. Okay, because I am representing the graph with vertices as 1, 2, 3, 4, 1. So j such that j is an integer j is an integer and j is less than or equal to 1, greater than or equal to 1 and less than or equal to n. As simply just in the previous case, recall that in the case of graph coloring problem, j is an integer and j is 1 to m, because here in that case each xi represents the color. Here each xi represent one vertex and all the vertex must be different. So in the case Hamiltonian cycle, our explicit constraints, this is what? Explicit constraints. Explicit constraints. Explicit constraint is that each xi is a vertex and all the xi's must be different. This is our implicit constraint. Implicit constraints क्या है? Implicit constraints. Implicit constraints means this is actually the solution vector. Again, just for every, if you take the state space tree, then if you start the cycle, then simply for the first position, just I am taking what? The first vertex, okay? And then how many vertices I am having? 2 to n. So here the x2, because here I am starting from x2, because I have assumed that the x1 is always 1. So in the state space tree, if we draw the x2 equal to 1, x2 equal to 2, x2. If you are not taking x1 equal to 1, suppose, then simply what? x1 equal to 1, x1 equal to 2, x1 equal to 3, x1 equal to 4. Suppose in the graph there are 4 vertices. So every node is having what? 4 branches. Okay? So simply just here there are n number of elements. So simply just here the factorial n or n ki power n, because for every position here x1 there can be what? The n. There can be for possibility this one is 1. Suppose I have taken here fixed. Suppose this is the n ways. This is what? N minus 1. The condition is that all the vertices should be different. So the possible x3, n minus 2 and so on. So here the size of the solution space is factorial n. The size of the solution space is factorial n. All permutations of the n, all possible permutations of n vertices. Okay? So implicit constraints here, what are the implicit constraints? Implicit constraints is no two xi's will be same. Okay? The first one, and second is x1 equal to 1. Just this I am taking to avoid the multiple cycle. Okay? So these are the explicit constraint, implicit constraint and the state space tree. Now I will give the algorithm. Okay? So here, see, you can check that this graph is not Hamiltonian. There is no Hamiltonian cycle exists. So this graph is not Hamiltonian graph. Okay. So now simply we write the algorithm, backtracking algorithm. Okay. So before generating the values for next vertex. Okay. See. Here, what is our objective is simply to generate the path. Path from what? 1, x1, x2, so on, xk minus 1. Suppose I have already generated the path from x1 to xk minus 1. Means if this is a path, if this is a path and this is Hamiltonian path, then all xi's are distinct. Means x1, x2, xk minus 1 all are different, and it is a path. That means x1 is adjacent to x2, x2 is adjacent to 2 and so on. Now our objective is to find the next vertex for xk. So first thing I have to check whatever be the vertex, that xk should be different from x1, x2, xk minus 1, first condition. The second, xk minus 1, if suppose the xk is after xk minus 1 in this path, because the path contains all n vertices, so xk minus 1 should be adjacent to xk. Okay. And next, what are the possibilities for xk? Xk can be generated from what? From 1 to 1 is already fixed. So simply xk can be 2 to n. It can be 2, 3, 4, 5, 6, so on. Okay. So here again I will use the same function, the mod function, like this. Xk in the next value, xk equal to xk plus 1 mod n plus 1. Remember that here not n plus 1. In the previous case in the graph coloring, here I have written m. M is the number of colors. Here I have written n plus 1. Now see the working of this. It will generate next highest numbered vertex. Suppose if the previous xk is 3. So next is xk is 3 plus 1, and suppose in your graph there are 5 vertices. 3 plus 1 mod 5 plus 1 6, so that is 4. It will generate what? 4. Next time again the same equation, same expression will be executed, then it will return 5, and again it will executed, it will return 0. If xk returns 0, it means that no vertex adjacent to it find, and the stack will be checked and the backtracking proceeds. Okay. So here in the solution vector, again the like M coloring problem, solution vector is declared globally, and the x1 will be initialized with 1, and all x2 to n means x2 so on xn will be initialized to 0. Okay? Will be initialized to 0. That is initially जो solution vector x होगा वो आपका ये होगा कुछ 1 0 0 0 0. If suppose in your graph n equal to 5, 1 0 1 2 3 4 5. Okay? So simply just here I am taking the first vertex as 1. Why I am taking 1? It is fixed. Simply to avoid the same cycle again. Okay? Repetition of same cycle, and all other component of the solution vector is initialized with 0. So automatically that expression will generate the next vertex, and whether it is feasible or not, it will check. So now I am writing the algorithm. Okay, and see this is very similar to the its functioning is very similar to graph coloring problem, so I don't think that there is any problem. But see, next value k, next value k. Okay, just here, if simply when this function is called, okay, first I will write what the function x k equal to x k plus 1 mod n plus 1. Okay, next value k, and while true. Okay, if xk equal to 0, then break from what? This while loop. Okay, flag. Suppose xk is not 0, then we have to check that whether xk is a feasible vertex or not. So what first I have to check that xk, because before calling this function, x1 x2 so on xk minus 1, ठीक है, path have already been generated. x1, x2, xk minus 1 is a path of distinct vertices. Now I am just finding the next vertex xk. So what is the criteria for xk? First thing, xk must be adjacent to xk minus 1. Okay, so how we check? If g x k minus 1 comma xk equal to 1. If this condition is true, okay, if this condition is true, it means, okay, just whatever the color generated by, whatever the vertex generated by this expression is adjacent to the previous vertex, okay, then only the xk can be added to this path. Okay, again, if the xk minus 1 and xk are adjacent, it means there is a in the graph adjacency matrix G, you can take here very small. Okay, so this is the xk is adjacent. Now next, this xk, whatever be the xk generated by this expression, should be different from all xi's, because this is a path. If this is a path, then all the vertices should be distinct. So here I will take flag equal to 1 for j is equal to 1 to k minus 1. If xj equal to xk, okay, मतलब कि जो xk जनरेट हुआ है वो अगर किसी भी x1, x2, xk माइनस वर्टेक्स के सिमिलर हो जाती है, जो भी xk में वर्टेक्स नंबर आई है अगर वो सिमिलर है, इट मीन्स दिस इज नॉट एडेड टू द पाथ. सो हियर flag equal to 0 and break. So it will come out from this for loop. Okay, and suppose just flag equal to 1, and it means if flag equal to 1 after the termination of this loop, it means that xj and xk are मतलब xk is different from all xi's from 1 to k minus 1. So if flag equal to 1, okay, so if suppose there are two conditions, either k is less than n. If k is less than n, it means that this is the next vertex to be included. And suppose if k equal to n, if k equal to n, then this is a cycle, Hamiltonian cycle, then xk should be equal to x1. So here, just here I will check if flag equal to 1, if k is less than n, if k is less than n, or k equal to n, k is equal to n, and see, if flag equal to 1, it means okay, the xk vertex is different from all the k minus 1 vertices have already been generated before calling this function. If flag equal to 1, if k is less than n, or k equal to n, if suppose this is a nth vertex, if it is nth vertex, then it should be equal to the first vertex to make it cycle. So, and here xg, I will check from the graph g, okay, xn equal to x1. this ये कंडीशन ध्यान से देखो, x1. See, just here the one condition is k less than n. If k is less than n, it's okay, just it will return. Yeah, here it is break. Okay, break from what? From while loop. Okay, and if suppose k equal to n, it means this is the last vertex. If this is the last vertex, then this should be equal to the first vertex. Xn equal to x1. If k equal to 1, then xn, or you can write here k, xk equal to x1, then only it will come out from the while loop. Otherwise, just this is not a correct, if flag is equal to 1, but this condition is not satisfied, then it will simply go for the other solution. Okay. Now, this is the bounding function for the Hamiltonian cycle, and now the main function is very similar to the graph coloring problem, M coloring, Hamiltonian. Okay? Hamiltonian K. From main it is called Hamiltonian 2, because for the first solution vector, first element I have selected as 1. So I will call this function from the main as Hamiltonian 2. Okay. So here first the here while true, next value k, if xk equal to 0, then it will come out from the loop. Else, if k equal to n, then write x1, one cycle you get. Okay. Else, again call Hamiltonian. Okay, Hamiltonian k plus 1. Okay, this is the loop. Next value k, and here the main function is what? See, the graph will be declared globally outside the main, void main. Here the graph int g 10 10 x 10 solution vector, and then number of vertices n is declared globally. Okay, so first you read the graph, g read. Okay, after reading the graph, simply you initialize the solution vector. Okay, so for j equal to 2, j less than, or you can take I equal to 2, I less than or equal to n, I plus plus. We told that ki except the first component, just 2 to n, solution vector is initialized with 0. Okay, and then the solution vector 1, x1 will be 1. Here I will fix the first element of the solution vector is 1, so that every cycle, Hamiltonian cycle, should start from 1. Okay, and then you call this function Hamiltonian 2. Okay, why I am calling 2? Because for the first solution vector is set, and then the value of k is 2. So here just simply for the, if you consider the all possibility, then here first it will check the what will be the next vertex for the second position in the solution vector. If suppose number of vertices are 4, then x2 equal to 2, x2 equal to 3, x2 equal to 4. Okay, so in this way x2 equal to 2, and if x2 equal to 2, then the x3 equal to 3 and x3 equal to 4, because all the vertices should be different. x2 equal to 2, x3 equal to 3, then x4 equal to, here I have taken n equal to 4, x4 equal to 2, 3, 4. Okay, and then this what here next. So in this way the node will be generated, and you can trace the program as the M coloring by taking the stack and calling next value function from Hamiltonian. Okay.